and sit on the other side of it so you don't have to turn around, that's fine.
So why don't you just put on the
Because it's not enough room to get through. They're out. See, they're sort of blocking the way now to lab, but we're not going to lab next. That's okay. All right, did I start that?
Is it 3-day lab or next class?
Yep.
Yep. 3-day lab? Yep. Oh boy. Okay, so you just have this 3 lab completed. This was lab 21. You already have time.
Okay, I think I pressed. Yep, it's already running. All right. Let's get going on this real quickly. It's not very long, it's class period, so I need your attention up front. Thank you. I basically printed out experiment 11 for you because experiment 11 in the book uses old school methods of doing Boyle's law and Charles' law, and we got cooler stuff than that you use at the college, and so we're going to use the cooler stuff whether we like it or not. It's a lot cheaper, and it's a lot more fun, and it works a lot better, so we're going to use it. So this lab it's actually a 3-day lab. It will go from January 24th, 28th, and 30th. We'll be doing parts of it. So sort of look ahead, look at it. It's not real hard. They're really easy, but you need to be able to be doing it. Also, on the 30th, we're going to have after-school review here from 2:30 to 3:30. I'm also going to have the Friday tutorial be a review for CE. Okay, for your test coming up. So, having said that, we're going to go ahead and get started with your notes. So if you grab your notes out from last time, remember that your daily work, I have included last year's lecture and this year's lecture, so you need another try. Yes?
So we're not running the lab, we're using this?
Unless you really want to.
No.
No. Thank you.
Okay, but you didn't get that from me. You did it on your own.
Yeah.
Okay. Just saying. Okay. Today we're going right here. There's problems in your notes. I want you to have a chance to be able to do them, so I put the solutions here to see if you can figure them out. And then you can go back here and check it. Okay? So we're going to go through the lecture. We're going to get started. Hey guys, stay with me. Okay, kinetic theory. I'm going to give you a way to remember it. Okay? There are several kinetic theory parts. Okay? Kinetic theory is all about how things move, how they interact with their environment, how they get into things. That's kinetic theory. Anybody know what the equation for kinetic theory is? What kinetic energy? No, well that's for energy. E equals mc squared is for energy. There's another one that's just specific kinetic energy.
Is it part of the kinematics?
It's 1/2 mass times velocity squared. It's kinetic energy. Okay? So we're going to talk about the kinetic theory. Whoops. Come on. Where is it? Okay, we're going to go here first. All right. So I thought, am I going backwards? I am. Okay, so kinetic theory. Toddler rule. This is how I remember it. Toddler rule. Tell me about toddlers.
Oh, they touch everything and they like cry a lot.
Okay? Touch everything and cry a lot. What else? They're messy, they're annoying. Tell me more about toddlers. Can't drink milk. What? Stick stuff in their mouths. Okay, so this is how I think of toddlers. Okay? They're like particles in an ideal gas. Everybody thinks, oh, they're so cute, right?
They are, but then they have their terrible twos.
Okay, so number one, they basically have no volume. So if you go to a show or you go on an airplane, they can sit on your lap. Okay, you don't have to pay for a seat. Okay. Second, they have elastic collisions. How many times do you see a toddler fall down and get right back up? Unless somebody's looking. If somebody's looking, then it's right? But nobody's looking, they'll look around and go, oh, yeah, that hurt a little bit. Okay, and get back up, right? Because they're learning to walk. So we call it elastic collisions. They are in constant random motion. Oh, this is cool. And they get here and they go, oh no, this. and they just keep going. They're like this constant movement everywhere. But it's straight line. They see something, it attracts their attention, and they get there, and then they get distracted and go straight to something else. Okay? They don't attract or repel each other. Okay? So let me tell you a story of my kids when I took them to the store when they were little. They had never seen a person of color. They had never seen a person with a tattoo until I went into this store. There was this big, large, black guy with rings in his nose and his ears and his lips and tattoos up and down. Oh, he wasn't scared. They weren't scared of him. He said, "Did your mommy get mad at you for writing all over you?" They weren't scared of him. They're not attracted or repelled. They're just another person. Why did you do that? You know, they just innocent. Okay, so they're not attracted or repelled. They don't look at you and say, "Oh, you're good looking, I'm going to talk to you." They talk to anybody, right?
So what did you guys say?
He was so cute. He was like, "Yeah, my mommy got mad at me for that, so don't you do it." He was really cute. Okay, they have average kinetic energy. Have you ever watched a kid? If it's cold outside, what do they want? Toddlers, what do they want? They want their blankie and snuggles, right? If it's nice outside, where do they want to be? Outside the playground, play and play some more, right? So, if the temperature outside is warm, their kinetic energy is high. If the energy outside is cold, their energy is small. Okay, they want to snuggle. By relating it to a toddler, I know what properties of an ideal gas are. Okay, so think in your mind, toddler rules, ideal gas. Okay? Everybody got your toddler rules down? Give me a few more minutes. Okay, this is how I remember it, because otherwise it's really hard for me to remember this 5. Remember, under 5 is considered a toddler, so you need 5 things. Okay, so that will help. But then they start to grow, right? Okay, so there's my toddler. He's so cute. I didn't do all these little pictures, but all these cute little toddler cool things. Get real. These are teenagers. Okay, this is what real gas is. Not ideal, but real gases are. Okay, so tell me about teenagers. Messy. Okay, let's look. Particles in a real gas. So this is where I think teenagers, okay? First of all, they have their own volume. They've got to now pay for their space in the movie theater or the airplane. They have their own space. Man, don't cross my space. You're too close to me. Get away, right? I need my space. Second, they do attract and repel each other. You like people, you don't like people. You have this attraction-repelling thing going on. Okay? You don't necessarily go up to everybody and ask them why they got writing all over them. Right? You have learned in driver's ed that collisions are not elastic. Okay? So you've gotten a little bit real. Okay, so there's only 3 for teenagers. Now, how can I get teenagers to behave more ideally? More like my stuff. A good old whooping, huh? Okay, first of all, low pressure. When is it low pressure? Summertime. So think summer, teenagers are ideal. Because during the year, man, we got pressures at school, we got the pressures at work, we got the pressures of family, and Christmas and all this other stuff going on. But summer, oh, right? It's warm. So low pressure. High temperatures. And when I get to hang with who I want to, not to, who's assigned to my class. So, I mean, non-polar situations. Okay, so ideally is when I can get teenagers to act like ideal gases, low pressure, high temperature, and when I'm in non-polar situations, I choose the peeps that I want to hang with. Okay? All right, everybody get this now, so far. So toddlers are ideal gases. If everything was perfect, toddler rules follow ideal gases. So they would move in straight line motion. They would, do all the 5 things we talked about. Okay. All right. So I like some graphics here. Attract and repel each other. Collisions are not elastic. And gas is most ideal. Real gases are most ideal in the summertime. Low pressure, high temperature, and I get to hang with who I want to.
Ms. Hell?
Yes.
So you said the toddler rules are like ideal gases?
Ideal gases. So if I go back here to toddler rules, right? These are ideal.
But real gases are what teenagers are.
Right. So ideal gases are my toddlers. So everything thinks they're so cute and they're just wonderful until you have to spend the night with them. Right? Okay. They are. They unconditionally love you and it's awesome. Okay, so then real gases are what is really happening. So real gases do have their own volume. They do repel and attract things. They do have collisions that are not elastic. When they bounce into each other, they don't bounce back with the same amount of energy. Some is given into that crash. Okay? But when I have them at low pressures and high temperatures, and they're non-polar, that's when I can get them to act like ideals. Okay? All right, so next up, we need to be able to define the following. Kinetic energy. Anybody have an idea of what kinetic energy is?
Energy and motion. Raise your hand.
Energy and motion. So something like this. Oh, gosh, wait. Okay, it can be in sound. It can be these little cars that you pull back and they go forward. Mine are sort of broken right now. It could be lighting a candle. Okay, some kind of energy. So this is when we're actually in motion. We're doing something. So kinetic energy is equal to 1/2 mass times velocity squared. Real easy equation. It increases where the temperature increases. So the more energy, the hotter things are, the more faster the gases move. Okay? So their velocity increases with temperature. Potential energy is stored energy. This is energy that we have stored. Just like when I brought the candle out here. The candle has energy stored in it. Nothing's going to happen to that until I light it. Then it will start using the energy that's stored in this candle wax.
That's when that turns into kinetic.
Same thing with my little car. I can pull it back, but unless I let it go, that energy is potential. It's stored. When I let it go, it starts moving. Same thing with the air horn. I won't honk it again for you. But batteries have potential energy, yes. Okay. Cohesive forces are things that hold things together. They are the attractive forces between particles. These are what are part of potential energy. They hold things together. Disruptive forces result when a particle is in motion, and it's associated with kinetic. So cohesive holds together potential. So I've got potential within me, but if I don't do anything with it, it's doing state potential. That's when you get in this class and you start learning, you start increasing your brain matter. That's when I'm using my kinetic. When I start studying, when I start working, when I start doing things, when I'm doing, that's kinetic. If I just stood up here and did nothing, that would be potential. Okay? So you've got different forces. Cohesive, that holds things together, does not release the energy. And then disruptive, which releases the energy, and you go forward. While you guys are still writing, I'm going to take a drink. Nice, it's finally melted enough that I can actually get water out of it. Okay, does this make sense? Does anybody need more further definitions here? Yes, ma'am.
So for like a roller coaster, would the going up part be potential and like the coming
The
down?
going up would be increasing
Oh, so
potential
kinetic.
energy, but you're moving, so it is kinetic, but
And
it's
like
negative
going down
kinetic.
would be potential because you're not doing anything.
So you would reach the top of the curve, that would be your highest potential energy, and then it would turn into positive kinetic energy. So going up, your negative kinetic energy, hit potential,
And those stars.
then positive kinetic. Okay? Pulling an arrow back is potential energy. When I let go of it, it's now kinetic. So I've got a negative kinetic while pulling it back. Then I stop, that's potential. Let go, kinetic. We okay to move forward?
And I wish.
How can kinetic go negative?
Kinetic energy is the energy of motion. So either I'm moving forward, kinetic energy, or I'm moving backwards. So as I'm going negative kinetic energy, I'm actually putting that energy into potential energy. So as I'm putting it into potential energy, when I finally reach the peak of potential, now I have to go forward, giving off potential energy as kinetic. So it's like storing it while I'm going negative. Like going up the hill, it takes a lot of energy. But now when I come down the hill, I'm giving that off. Yes.
Kind of like bungee jumping or something when it goes down and up.
Like an elastic, yeah.
So when you gain more energy going on the downslope of it?
You're gaining kinetic, losing potential. So I hit the bottom, I have a maximum kinetic.
So you said you're going negative because you're putting N into the potential.
So I'm
And then when you let go and it goes into kinetic, would you gain any more or would it be like same exact amount?
So I'm putting into potential and not gaining any kinetic. When I get here, I'm now gaining kinetic, losing potential. All right, let's go forward. So here's this ball. I'm going to toss it up in the air. Okay? Suppose a toy ball is thrown up in the air such that it goes straight up and straight down. I did a little loop here because I want to be able to show you what's going on. Okay? It's caught by the same person. Describe the form of energy that occurs in the ball from the time it's thrown to the time it's caught. So remember, kinetic energy is 1/2 mass times velocity squared. So as it's going up, okay, I have initially given it so much energy, right? And it'll start slowing down, and then it gets to the top. So I had kinetic energy, and then I stopped at this top point. That's potential now. Total height of potential. Then it starts coming back down, gaining in kinetic energy again, until it's equal to what I gave it to start. Yes.
Sorry, dumb question, but
No, don't question.
is it 1/2 of m times v squared
Right.
or 1/2 of mv squared?
So just the v is squared, just the velocity is squared. Okay? It's 1/2 times this whole thing, so 1/2 of this whole thing, but this is mass times velocity squared.
do that square first, the rest doesn't matter which one you do.
Right. So if you do velocity squared times mass, then divide it by 2, then you got your answer. Order of operations. Okay? All right, second thing. Now you got well, sorry, go ahead.
Would, like when the ball's in the kid's hand, would that be potential energy?
So it'll be potential, yep. So then the minute I put energy in, I put kinetic energy for me into the ball. So then as it loses the potential, or kinetic energy gets to the top, it's potential again. Then it goes back down, increasing in kinetic till I hold it, and then time I catch it, it's not potential. Right? So anytime it stops, it's potential. Anytime it's moving, it's kinetic. Okay?
So how would we solve that because we don't know the velocity?
We couldn't solve it, we could just say. Now I'm going to give you one you can solve. Okay? So here's a football one for those who like football. So suppose a 180 pound, which is about 81.8 kilograms, halfback running at a speed of 8 meters per second collides head on with a 260 pound, 18.2 kilograms, tackle running at 3 meters per second. Which one will be pushed back? That is, which one has more kinetic energy? So we're still using the equation 1/2 mass times velocity squared. 1/2 mass times velocity squared. Would you quickly use your calculators? If you need a calculator, come up here and figure out how much kinetic energy each one has. We're going to make this one 81.8 kilogram, running at 8.0 meters per second. And this guy right here is the 118.2 kilogram, running at 3.0 meters per second.
This is in units of joules, right?
You're going in joules, yes. Yes.
That's not gonna confuse it.
So you want to pick a velocity first. So for this one, we'll do 8 times the mass.
Yeah, that's what I thought.
Yeah, this is good observation here. You want to put the problem in backwards. So do your velocity, square it, then times it by your mass, then divide it by 2. Okay, unless you got it in order of operations. And you gotta be careful with a square because it wants to square that whole thing. And it's not the whole thing is squared, just the velocity.
Do what? So you half it last?
Half at last.
Okay, so you need to speak on it.
Okay, so what do we give for this guy? What's his kinetic energy?
2,617.6.
Oh, I heard 3 different answers.
2,617.6.
Yes?
Joules.
Okay, we'll just do that. We've got about 3 significant figures carrying one more. How about this guy? What's his kinetic energy?
531.9 joules.
531?
31.
God, he made me put 39. Jesus Christ.
Okay, so this guy, even though they're a lot lighter, has more kinetic energy and will actually push the other one back. Okay?
It's gonna go
All right, so this one is going to push this one back, and then see how far we can figure out how much, but we're not going to do that.
ratios, right?
Yeah, it's sort of. Okay, this one has a lot more energy behind it than this one does, by about 5 times. Okay, all right, now let's look at this. And you guys gotta keep me on track here. What time do we get out of here? 1:41. Okay. So which would travel a greater kinetic distance? This is sort of you got to think in your head. Okay, a hydrogen molecule. So how does hydrogen hang around? In pairs. Thank you. H2. So what's its mass going to be? What's the mass? 2 times 1.008, which is 2.016, right? Traveling with a velocity of 2v. So that's the velocity is equal to 2v. Or helium molecules. Helium molecules weigh 4.what?
It's unpredictable where they're going.
4.0026, traveling with a velocity of v. So I have not given you the velocities. Okay? Which would have the greater kinetic energy? So now you got to sort of do math algebra. It's not hard. Okay, remember the equation? Kinetic energy equals 1/2 mass times velocity squared, right? So we're going to put that in there. We're going to put that in there. We're going to get an answer. So if I put that in, I'm going to get 1/2 times 2.016 times 2 squared is 4. V squared is V squared. So I'm basically going, that 2 will cancel with that, leaving 2. I'm 2 timesing it basically. Over here, I'm going to go kinetic energy equals 1/2 4.0026 times V squared is still going to be V squared because V is equal to V. This will be about what? 2.013 V for the kinetic energy over here. And over here we get what? 4.032 V squared. That has more energy. Yes. This came in right here. 2V went in for V and it's squared. So
why is that?
2 squared is 4.
Why is that 2b? Like why is V?
That's what they gave me.
Oh, okay.
So they gave me, yeah.
So why isn't helium 2?
Why isn't helium 2? Because helium is not a diatomic. It's not one of our ones that hang around in pairs.
Oh, why'd you take out the square for the helium?
I didn't. I just said the velocity here is, oh, it should be squared. Sorry. Thank you. Didn't carry it down. Okay, any questions with this? Do you see my math? It's not magic math, it works really. Any questions with how to get that math and what I did? There will be problems like this. They might not choose hydrogen and helium. Kyle, will you shut that door behind you? Right behind him in the corner, remember, are the twins, the quadruplets, and the octets. You need to know these. Okay? So bromine, oxygen, nitrogen, hydrogen, iodine, fluorine, chlorine. With kinetic theory, we're talking about gases. So which one of those would not be included? Who knows? There's 2 of them that will not be included.
Oxygen and hydrogen.
No, those are gases.
Oh.
What ones are not gases?
Iodine.
Bromine and iodine, right. So bromine and iodine we can't use kinetic theory. Okay, what about phosphorus and sulfur? Are those gases or are those solids? Solids, so they don't count either. So kinetic area is all about gases. Okay? So it has to do with gases. All right, going forward. This becomes really, really important. You need to know these conversions. She will use them backwards and forwards on your test. I would write them down. I would put them on my 3x5 card. They're also on the back of your periodic table. Sorry, I'll get out of your way. Just tell me when we can't see. They're up at the top. They're on the back of your periodic table. But you need to know all the conversions that are up there on the board. Not all of them are on your periodic table. You need to know how to go backwards and forwards. Here's a hint. If you're using my TI-83s, or if you've got a TI-83 or a TI-84 plus of your own, go to Side Tools. Under Side Tools, there's a thing that says pressure. And you pick pressure. You put in what you have, and it will give you what you need.
Oh, that is very useful, actually.
So Side Tools is a conversion factor. So if you need to go from meters to millimeters or micrometers, it's there. If you need to go from grams to kilograms, or you need to go from ounces to grams, it's there.
So side tools?
So you go into apps, all apps, and then down to Side Tools.
Check, make sure I have all those.
Okay, so apps, and then you just go alpha S. I can't do my alphabet. Alpha S gives you Side Tools. Make sure you choose it in English. There's France and Dutch and Spanish and all kinds of weird ones. And then it just comes up with the Texas Instruments. You hit another button here, and then it says, do you want a scientific or scientific calculator? Ooh, for the end of year test that we have, she's going to dig you on scientific calculator. You know to calculate numbers and give the right numbers to your figures. It's right there. You just put it into the calculator and give you the right numbers.
So 18.
Okay, there is unit converter. There's a data graphics wizard. There's a vector calculation. We don't use the vectors.
Oh, nice.
Okay, so that's pretty interesting, cool thing to do. Okay, so you saw the gas particles collide here in the little animation that was here. You need to be able to go back and forth. Okay, so this is something like a problem that you would have on a test. A weather reporter on TV reports the barometric pressure is 28.6 inches of mercury. Calculate that pressure in the following. So, if you haven't got one of my calculators, come get one. Or if you got 184, great. But come get this so you can practice it. So you can do it on the test with no problem. How many do I need to bring around?
Uneducated.
Oh, I didn't mean to do that. Sorry.
I have one. Which calculator version are we using now?
Okay, so first you go to apps, and then Side Tools.
So this has French, but not science. Literally has French.
Okay, everybody got the right tool? Apps and Side Tools. Everybody got it? So I don't like to arrow down. So I just hit apps and then I do alpha, and the S is the stow button. This one doesn't have it. So that's one of the first things that I would do is make sure that my calculator that I grabbed from up here had it, because this one, it's erased.
What is it called?
Side Tools. Oh, there it is. It's just under. Interesting. Okay, then you just press enter once you get to Side Tools. Everybody got that?
Yeah.
Okay, now we are going to be using pressure. So I'm going to use a unit converter, which is number 2. So I arrow down to number 2, hit enter. I am working with pressure. Okay, apps,
Holy
and then
crap.
go alpha, stow, which is S. And you should bring up Side Tools. So S should be the stow button. Okay, so now what you want to do is you want to choose pressure. Which one's pressure? What number? 9. Press 9. Then what do you want to do? You want to put in a 26 or 28.6 and then put the unit inches after it.
Inches squared?
Just inches. Yeah.
How do you put inches? NH2, NH9, NH.
Yeah, there's no inches.
I got it.
Pounds per inches squared. Yes, pounds per inches squared. Okay.
28.6.
Now, as an arrow, what do we want to get to? We want to try and go to atmospheres. So find atmospheres on the bottom, arrow to it or whatever. ATM. Hit enter. That should give you an answer. What is it?
1.94615.
1.996.
946
946
115
times 10 to the
0.
10 to the 0, so I can drop that. So this is atmospheres. Now I want you to put it again. 28.6 inches mercury. Where do you get?
Ms. Hall, do we do significance or no?
This helps.
So if you can't do it by doing alpha S, you're just going to have to scroll down to where you can see side tools. It takes a minute, but it's okay. So you just scroll down to it says side tools, hit enter, press it again. You're going to unit converter number 2, and then you want to do 9.
No, that's not right.
Okay, so 28.6 inches,
You want? No.
inches mercury.
Oh, you have pounds. So why do you think it's where it's going to
So is this not what we got, everybody?
Wait, if you convert 28.6 inches of mercury to PSI, not the other way around.
Which one's
Right, you're going inches to atmospheres. So make sure you put your inches in first. And, oh, sorry. It should be inches of mercury. Did we not have inches of mercury?
She just
No, inches of mercury is up in the far. You should have INHG is what the way inches mercury is.
Wait, that's what we should have been using the whole time?
So 28.6 inches HG. Okay? And I believe there's 14.6 inches HG in 1 ATM. So you can also convert it that way. Okay, what did we get? I didn't hear the right answer.
1.956.
1.956.
No, 0.956.
0.6 atmospheres. Okay, you should be able to do the exact same thing with torque.
There's no torque on there. There is a torque.
Torque is the same as millimeters mercury.
I was about to say that.
Okay, so there's something that you do have to know in order to use it. So torque is the same as millimeters mercury. It's just the guy's name that invented that form of measuring millimeters mercury. So all of these are right here, and you're basically just doing the conversion factors. I just showed you the shortcut with the computer. Okay, we'll continue here next time. Have a good day, guys.